Today we're going to talk about quantum mechanics. Just the phrase quantum mechanics tends to evoke either extreme curiosity or abject fear in people. And it is a mind-bending concept, but it is also fascinating. The first developers of this theory were not necessarily excited about what they had discovered. Erwin Schrödinger, famous for his thought experiment about a cat in a box, said, "I don't like it, and I'm sorry I ever had anything to do with it." Niels Bohr, famous for his model of the atom, said, quote, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Your theory is crazy, but it's not crazy enough to be true." So let's look at that truth. To understand quantum mechanics, really it's easiest to start with light. Light is a really interesting phenomenon because it's shown to have what we call a complementary property. Light acts like a wave, and it also acts like a particle. The problem with that is that this is contradictory. So let's look at the definitions of a wave and a particle and see how they contradict. A wave is defined as a disturbance that travels through a medium. Now here's the important part: transporting energy from one location to another without transporting matter. A particle, on the other hand, is defined as an object with properties like volume, density, mass, aka matter. So light acts like a wave, which in its definition is not matter, but it also acts like a particle, which definition is matter. Perfect, this isn't confusing at all. But actually these complementary properties are not all that unusual. And the thing about complementary properties is that you can definitively prove that both of these contradictory properties are true, but you can never prove it at the same time. So with the wave-particle duality of nature, we can prove that light acts as a wave, and we can prove it acts as a particle, but never with the same experiment. So today, we're going to prove that light acts like a wave. Waves have distinctive properties that particles do not. One of these properties is called diffraction, which basically means if a wave encounters an obstacle, it will bend around that obstacle. So if you imagine a wave passing through a water medium, if that wave were to go through a small opening, the wave would actually bend around the opening. A particle doesn't do this. If you pass a particle through a narrow opening, either it passes directly through with its direction completely unchanged, or it bounces off the sides and changes its direction. But either way, it travels in straight lines. Now, another key property of waves is called interference. This is where a wave interferes with another wave, and the wave can either interfere constructively and build the height of that wave, or it can interfere destructively, and actually the waves would cancel each other out. Now, particles can't do this. If particles interact with each other, they just smash, and then you apply the normal laws of physics. Now, if you pass a wave through two small openings, it will bend as it goes through both of those openings, and then it will actually interfere with itself on the other side of that opening, creating an alternating constructive and destructive interference pattern for the wave. Now, if you do this with light, you'll see an alternating bright, dark pattern. This groundbreaking experiment that ended centuries-long debate about the nature of light is called the double-slit experiment. So today, let's do our own version of the classic double-slit experiment. All you need is like a little laser pointer. Okay, so I found a closet where we can test this out. Before we make our double-slit experiment, we're just gonna take our laser and shine it on the wall so we can compare what it looks like beforehand and after. All right, so I'm gonna turn out the lights and I'm gonna shine the laser on the wall. So we're gonna use this wire to make our slits. I'm gonna put the wire right over the mouse, or right over the laser, and then I'm just gonna tape it down. Next, I'm gonna take two little pieces of this electrical wire and I'm gonna put them up really close to the wire, but not quite touching it. And that's how we're gonna make our slits. Okay, so I made a slit. Make sure there's space on either side of your wire, just a small slit. All right, so let's turn the light out and see how we did. So I'm gonna turn it on now. See that alternating light, dark, light, dark, light, dark pattern? We've proved that light is, in fact, a wave. It probably doesn't shock you that light is a wave, We've been inundated with images of light as a wave since we were children. But just like light has a wave-particle duality, so does matter. In fact, if we had a little bit higher tech equipment, we could do this exact same experiment with electrons. If we sent electrons through the slits, just one electron at a time, we would see the exact same diffraction pattern, which means each electron is going through both slits at the same time and interfering with itself on the other side. Quantum mechanics is weird, but it is key to understanding electrons and chemical reactions. The fact that electrons, just like light, have the same wave-particle duality has fundamentally reworked the way that we understand chemistry. And it's allowed for all kinds of technology, like the electron microscope, for example. And it's paving the way for new kinds of technology that are just on the horizon, like quantum computers. And that's it for this edition of Chemistry in Real Life.